you, maybe you think too much, 'cause you're Hollywood, you never should, we never talk anymore.
So an example would be, let's see, have an example. Okay, so we're given that F, vector field F is equal to the curl, I always do that, curl of another vector field A. So A is the vector potential. So then we have A, this is a given, A is equal to y plus z, comma, sine of xy. And the last one is e to the xyz, all multiplied together. So what we're supposed to do on this one is it tells us to find flux of F through S, where C, and I'll draw a picture to supplement this, where C is the unit circle on or in the x, not xy plane, but the xz plane. Okay, they threw in a little twist here. Okay, so this is what they give us, as well as a picture. Okay, so we have our x, our y, and our z, and we have a unit circle going on the x and z plane, and so this is oriented like this. That's what the picture says. And then we have some surface S attached to it. So this is S, all right? Okay, so let's get started. We have our given information. So we know that F is the curl of A, which is useful. And what we can do is start writing relations, in this case, specifically using Stokes' theorem. So what we can do, start off with, is the line integral over C. We'll call this C. This is the unit circle. Right? So the line integral over C of A dot T ds is equal to, by Stokes' theorem, the double integral or the surface integral of the curl of A dotted with the normal vector ds. Okay? And this also equivalently is equal to the surface integral of f dot n ds, and this right here is the flux. So this is what we're trying to get to. So basically what we can do is work through this side here. Okay? Alright, so flux is equal to this thing as well as this thing as well. Okay, so to begin computing the line integral, we have to first parameterize the curve C. So we're going to parameterize C, which is equal to the boundary of S, right? This is its only boundary here. Okay, so by parameterizing C, we're going to, this is the unit circle in the xz plane. So that would give us unit circle, so that means a radius of 1, so 1 times cosine t, and then nothing, it has no dimension on the y plane, on the y-axis, so that would be a 0 there, but then we'd have our sine t on the z-axis. Okay. So then c prime of t, let's take the first derivatives of each of these components. So we get a negative sine t, a 0, and a cosine t. Alright, so now what I'm going to do is compute the a of c of t dotted with c prime of t. Okay, so for a, we're given this at the top, right? So we're going to plug in our x, our y, and our z for each of them. So what we do is y plus z is 0 plus sine t. And then for the second component, we have a sine of x times y, which would turn out to be just a 0. And then for the last one, we have e to the xyz, which, because the y is 0, that would turn out to be e to the 0. And then we have it dotted with the c prime of t, so dotted with negative sine t, 0, and cosine t. Alright, I'll continue this on the next slide. So what we get is a sine t, comma 0, comma 1, because e to the 0 is 1, dotted with a negative sine t, a 0, and a cosine t. Alright, so this is equal to, let's see, what do we have? A negative sine squared t, and then plus a 0 plus a cosine t. All right. So then when we set up our integral, so again, our bounds for the unit circle are going to be from 0 to 2 pi because we want to go all the way around, right? All the way around the unit circle. So when we set it up, we get 0 to 2 pi. These are our bounds on our parameter variable. And then on the inside, we have this stuff, which just reduces to a cosine t minus sine squared t, and then a dt. Okay? So from here, as I've said before, whenever you have a single cosine t or cosine theta, or sine t or sine theta, and you're integrating over a full period, so from 0 to 2 pi, it's going to go away in the integration. This is eventually going to become 0, and you're welcome to try it out and go through the calculations, but it's going to turn out to be 0, this component. So what we're left with is a negative sine squared t. So let's use the double angle formulas that we know of. So we know 2 sine squared t plus 1 is equal to cosine 2t. Here's our double angle formula. And to solve for a negative sine squared t, what we'd have to do is subtract this over to the side. So then basically what we would end up with, by doing a little bit of manipulation here, is negative sine squared t is equal to 1 minus cosine 2t divided by 2. Okay? So that's what we're going to replace this with. So I'm going to write in a 1 over 2. I'll just bring that out in front automatically. 0 to 2 pi. And then 1 minus cosine 2t. And then a dt at the end. Alright? So now I'm going to break this up into 2 so we can work with them separately. So we have a 1/2 times the integral from 0 to 2 pi of 1 dt minus 1/2 and then 0 to 2 pi of cosine 2t dt. And this becomes, let's see, if we do u substitution, that would be u equals 2t, and du then equals 2 dt. So dt equals du over 2. When we plug that in, we'll simplify this one first. So we get 1/2 times t as t goes from 0 to 2 pi minus 1/2, and we're going to get rid of the bounds because we're switching into u's now. So we get cosine of u, and then dt is now du over 2. So that turns into a 1/4 in front. So we get a 1/2 times 2 pi minus 1 over 4, and then in the integration, this goes to sine u, okay? And I'll continue this on the next slide. So what we get is a pi, and then minus 1 over 4 sine of 2t. I'm going to replace those in, replace the t's, so then you can replace the bounds. So it's like that. And then this turns out to be pi minus 1 over 4 times sine 4 pi minus sine 0, which these both go to 0. So our final answer for this is going to be just pi, a single 1 pi. Okay? Alright, so now one last thing. You might be wondering, like, what is this curl thing? So an interpretation of it, so interpretation, yeah, there we go. It's been a long day. So an interpretation of it is that the curl tells us, curl tells us it's called the circulation, so how much something is going around, per unit of enclosed area, and I'll explain a little bit. I won't go too much in depth. This is just the what it signifies in each tangent plane at point P. Okay, so what I mean by this is that let's say you have some graph here, right? And then we have here's our boundary, and then here's our surface. Something crazy like that. Okay, so basically the curl is, let's say you're at point P here, okay? So you're on point P, there, and what you have at each point to the surface is a tangent plane created. So the tangent plane here would look something like that, and it touches only at this one point. It touches the surface only right there. And what it does is it, in the calculation, it creates like a little enclosed area, okay? And then here's our little normal vector. And again, like I said, you don't have to know this like by heart or anything. I'm pretty sure that the professor's not going to ask you, like, what does the curl signify? If he does, this is great. This is a good background. But anyways, so here's our tangent plane, and then here's the normal vector. So basically what it's saying is that going around this enclosed area here, how much is, it's kind of like, think of it as spinning, sort of like a whirlpool. How much is going around in a circular motion around that point, basically. So anyways, that was my attempt at giving you guys a background on the curl. That was fun. Just, again, remember the formula for that. Remember curl of something, we'll just call it F, is equal to, and you're going to write 3, 2, 1, so F3, F2, F1, and another 3, 2, 1, okay? And then also, you're going to put in the little letters, so that would be, you start with Y, and then you go to Z, Z, X, X, and a Y. And then you have to add in at the last part, a minus sign, a comma, minus sign, comma, minus sign. Okay? So this is the formula for the curl when your given vector field is F sub 1, F sub 2, and F sub 3. Alright? So that does it for this video on Stokes' theorem. I wish you guys the best of luck, and the problems may seem a little bit hard at first, but don't worry, never fear. A challenge is always good, and then when you overcome it, it's pretty rewarding. So I'll talk to you guys later if you watch the practice problems video.
I could never keep track of who's gonna come when you start waving your magic